Yeah, it's okay.
Okay. Yeah. Thank you very much. It's my great honor to give a talk on this very nice second international conference on massive gravity theory and the physics of black holes. And my name is Lijing Shao, and I'm very particularly thankful to Ame and Sabaham for inviting me to give this talk. And actually, before I start my talk, I will just give one slide to show you where I come from. So I come from the Kavli Institute for Astronomy and Astrophysics. And actually, it's a relatively new institute established in 2006, and it is jointly supported by Peking University and the Kavli Foundation. So it's in Beijing, China. We have quite many people. We have about 20 faculties here and work on mainly 4 areas in astronomy. So my research area is here is the gravitational physics and high energy phenomena. Okay, so I have a very small group here in the Kavli Institute, and we try to use astrophysical observations to understand the gravity theory and to test the fundamentals of gravity theories. So for the talk, let me start with the landscape of modern physics. So as we know, currently the modern physics from theoretical view of point is composed of 2 frameworks. One is the standard model of particle physics. So here is the Lagrangian for this very nice, beautiful standard model. And this Lagrangian can predict a lot of experimental output. So the language to describe this framework is called quantum field theory, so which is developed in the last century and is a very, very successful theory framework. On the other hand, we have general relativity, which describes the gravitation and space-time. Is also developed in last century by Albert Einstein, and he imagines the space-time as curved, and this curvature is a manifestation of the gravitational force. So here is the field equation from the general relativity. It describes the gravitational force in the universe at small scales and also at larger scales. So these 2 frameworks, they are very, very beautiful, and they are our fundamentals for the modern physics for the modern physics subject. Okay, so in this slide, I just show you the Lagrangian that is all of the our current understanding of the universe. So here, the first part is the Lagrangian of 3 fundamental forces, which is strong force, weak force, electromagnetic force. And this is, as I said, the part of standard model of particle physics. So it's a very beautiful framework. And on the other hand, we have this gravitational interaction, which is described mostly by this Ricci scalar R. And if you do a variation to the metric field for this action, you will get the Einstein's field equation. So basically, this is what we have known for the past century, and this is really the condense of our wisdom from the human being. But however, although on one hand we have the quantum field theory to describe 3 fundamental forces, and on the other hand we have general relativity to describe the dynamics of curved spacetime. But this is not the whole story, because there are some incompatibility for these 2 frameworks. So the quantum field theory and the general relativity, they are not compatible with each other. So this is one of the main unresolved question in physics and in particular for theoretical physics. And many people are working on this. They try to find a unified theory to describe both this quantum field theory and general relativity. So they, but no one has succeeded yet to find a fundamental theory which we have a name is the quantum gravity theory. But we have not reached this theory yet. So let me give a short summary for what I have said. So theoretical physics is very beautiful. It's very beautiful, and which is the main, the most successful science in the last century, and even in the past hundreds of years. But it's not yet complete. So we still have a problem to describe a unified framework for the whole area of physics. So in this paradigm, the gravity may be holding the key to a next level of our understanding for the physical world. Because here you can see the four fundamental forces. The gravity force has a very, very unique position. Okay, so what I will tell you today is that we try to use pulsars to test gravity theory, and this is a very very powerful means to do gravity experiment. So let me introduce you what are pulsars. Pulsars are rotating magnetized neutron stars because their rotating is so stable, and they appear as lighthouses for our radio telescopes. And we basically, this lighthouse effect provides some fundamental clocks for the observation. And the first thing I want to let you know are that pulsars are clocks. And because this is due to the stability of their rotation, you can count each rotation of pulsar's spin. But they are not only just clocks, they are very precise clocks. So this here I show one example. We have more than 3,000 pulsars in the sky have discovered. This is just one example. I show you the measurement of this rotation frequency. So this is from a data release by the IPTA collaboration. But there are also many other pulsars. They also show similar precision to their spin frequency. So here the last digit is the uncertainty for this last digit. So this is really, really amazing. So because the pulsars are so far away from us, but we can still measure the spin period to such a high precision. It's very different from the other area of astronomy. So basically astronomer, a lot of field of astronomy, they are order of magnitude estimation. So here for pulsars, you can really do very precise work. So how we get this precision? So the technology is called pulsar timing. So basically, we have large radio telescopes on Earth, and we observe these pulses for every rotation of the pulsar. So if these pulses arrive at the radio telescope, we record the so-called time of arrival of the pulse. So this is really, really a very simple experiment. You just record the times of arrival of these pulses, and then try to do physics. So as we know, the radio telescope is orbiting the sun together with the Earth. So we have very well understood physics for this solar system dynamics. This motion will affect the times of arrival because of different effects from the geometrical, the geometry and the Doppler effect. Also, if the pulsar, if it has a companion star, then they will also in their orbit, and this orbit will also affect the times of arrival of the radio pulses. So basically, the pulsar timing they are affected by the solar dynamics and also the orbital dynamics of the binary. There is some other effect from interstellar medium as well, but we can take care of them by using observations made at different frequencies. So by using this, so here I just show an example of the largest radio telescope on the Earth. So this is the 500-meter spherical telescope. It's called the FAST telescope, which is built in China. It is now the largest one in the world. So before this, it's the 300-meter radio telescope in the US. Now that one is broken, and this is the only one that is several hundred meters in the radio. So this telescope, they record the radio pulse from the pulsars and do the pulsar timing experiment. Okay, so why the pulses are particularly interested for gravity test? So let me introduce a theorem by Pinus. So we call it the Pinus Theorem. So Pinus Theorem says that neutron stars, they are superstars. So because neutron stars have a lot of super properties, these neutron stars, they are made from very dense, from super dense material, which is the density is larger than the nuclear matter. And they are also induced with the super strong gravity theory. So, neutron stars, they are almost black holes. So we need a general relativity to take care of the structure of neutron stars. They are also super fast rotators, and the faster one, the most rapidly spinning one is the spin period is about a millisecond. So they are also super precise timer because of the pulsar timing technology. We usually need more than 10 digits to describe the spin period. They are also exhibits some interesting effect like the super glitching and the superconducting and the superfluid in their interior. So they are very good to study many interesting physics. They also have a super strong magnetic field that is responsible for the generation of the radio pulses. In addition, neutron stars are also super rich in physics, because in neutron stars, you really have to take care of all the 4 fundamental forces that I mentioned before. You also need to take care of many effects from nuclear physics, particle physics, as well as condensed matter physics, plasma physics, hydrodynamics, and so on. So there are also many observations for neutron stars. And finally, they are also born in supernovas. So this is a very cute theorem, say that neutron stars are superstars. And because neutron stars, they are extremely, extreme in many aspects of physics. So they are very good laboratories to test fundamental theories. So one aspect is the strong field, which I will tell a few examples in the next slides. So the other part I will not touch upon, but I will just let you know that the pulsars are also extreme laboratories to test super nuclear matters. They are also very good to test some astrophysics. Okay, so now I will focus on the test of gravity theories with binary pulsars. So if a pulsar is in a binary, the word line is like this pupil lines here. So the green line is the binary, and we have the Earth around the sun here. So basically, by doing pulsar timing, you try to connect to proper time from the pulsar and from the radio telescope. This is the so-called pulsar timing model, and this connection is affected by the orbit of the radio pulsar. For example, if they are in a binary, they will have this precession, and the precession in some cases can be very large, much larger than the precession by the Mercury. And also because as we know in general relativity, there are gravitational radiation, and at the boundary we are radiated gravitational waves, which takes away energy, then make the orbital smaller and smaller. This effect can also be tested by this pulsar timing. And if the pulsar is behind the Pompeian star, and the radial pulse on its way to the radio telescope will experience a curved space-time produced by the companion star. So this is called the Shapiro delay. It's also measured in binary pulsar systems. So there are many other effects, relativistic effects, that can be measured by this pulsar timing experiment. So this here I just have 3 examples. So let us see how precise we can do the gravity test. So here I just show you some numbers. Let's focus on this red box, which shows some precision in testing general relativity. So for example, for the pre-Austrian advance, so in one binary pulsar system, we have measured the precision to the precision to such a high precision. So this is more than 4 degrees per year. So if you compare this with the Mercury, it's much larger. Mercury is 43 arcsecond per century. So this is per year. This is degree. So it's much larger. You have a much more relativistic system here. Also, you can measure the shrinkage, the orbital size reduce due to the gravitational wave emission. This precision, as you can see, can reach 7 millimeters per day. And these objects are a few thousand light years from us. And we can still measure such a precision. And we can monitor them for many decades. So this is a very good experiment to do this kind of test. So the measurement involves the so-called post-capillary parameters. So here I show some examples. So here, for example, this one is the precession rate for the pre-Austrian, and also you have this, as you can see, this is the time derivative of the orbital period due to the emission of gravitational waves. So here you have a triple mass, as we know from gravitational wave community. So you can measure basically all these parameters and to a very high precision. And because these parameters, they only depend on the right-hand side, they only depend on 2 unknown masses. So you can probe these. If you have measured one parameter, you can plot a curve in the mass diagram, which I will show you example here. So here, for example, if this is the Husted pulsar, by the way. So for example, if you have measured the omega dot is the pre-Austrian advance rate. So you can put a curve here because this depends on the mass of the pulsar and the mass of the companion. The sum of the total mass of these 2 things. So you have this very nice straight, very nice line here. And if you measure another parameter, you get another line. And if you measure a third parameter, and because this theory, the gravity theory, have to be consistent, so they must have to meet at one point. So in this sense, by measuring more than 2 parameters, you can start to perform gravity test. So this is actually the first test of the existence of gravitational waves, and by the Hus and Taylor, and they also got a Nobel Prize for this work. So the measurement really shows that they meet at one point. Okay, so now the best player in this field is the double pulsar. Actually, double pulsar, the group of double pulsar. So double pulsar here means we have a system observed is a binary and 2 neutron stars. Both are observed as pulsars. So actually, yesterday this plot came out. This is a publication by Kramer et al. This only came out yesterday in the Physical Review X. and they have really, this is the mass of the one pulsar, pulsar A. This is the mass of pulsar B. They have a lot of measurement here, and the width of these lines, they show the measurement uncertainty. As you can see, so many measurements, they really meet at one particular point, which means here the underlying gravity theory, which is general relativity, has passed many tests in this one system. So if you really want to look into this point, you have to zoom in by a lot. And here we show a zoom in plot. So here you can see within the measurement uncertainties, there is really indeed one point, and these measurements all meet at one point. If you want to have another gravity theory to describe this experiment, you also have to design very carefully a gravity theory that make these curves meet at one point. So this is very difficult actually. So this is one of the best tests in the gravity community of the general relativity. So the paper only came out yesterday, and you can find it on many social websites or the Physical Review X website. Okay, so I have said many things, and I wanted to have a quick summary of what I said. So here I have shown you that by using the pulsar timing technology, we are very, very sensitive to the binary motion. If a pulsar is in a binary, so we are very, very sensitive to the tiny change in orbits of binary pulsars. In this sense, binary pulsars, they are excellent test bed of the gravity theories, because different gravity theory, they will predict different changes in the orbit. For example, now I will give you two examples in massive gravity theory, which is the main topic of this conference. So before that, I will just show you one last plot. This shows the prediction of the Einstein's gravity on the per-Austron time shift. So what does this mean? So if in the Newtonian gravity, two orbitals, they are in the capillary orbit, and the per-Austron point is always fixed because the Newtonian gravity has the SO4 symmetry instead of SO3. So they will predict So they will predict a fixed per-Austron time shift. So by every orbiter, you go to the same per-Austron. But if in general relativity, because the orbital size is getting smaller and smaller, and the orbital period is getting smaller and smaller as well, so you will get to the per-Austron time earlier and earlier by each orbit. So this is the green line here shows the prediction from Einstein's gravity. So the white dots here are the data actually, the data from the measurement I just told you by the double pulsar observational team. So as you can see, the data fit the Einstein gravity very, very well, very, very well. Actually, I also wrote a physics viewpoint for this particular paper. It also came out yesterday. So this shows a very, very good test for the general relativity's quadrupolar formula for gravitational wave radiation. So this is will be useful for what I will tell you afterwards. Okay, now let's turn to some theory side. So let's first look at a toy theory, which is the linearized field Pauli theory for massive gravity. So this is a linearized theory. So we don't have orders. So this is H is the perturbation of the metric, and we have slew away the higher order terms for this H. So Finn and Thornton has worked out actually the most general linearized gravity theory with a graviton mass term. So the black part is from the general relativity. So if you just do an expansion of the Ricci scalar, you will get these black terms. And this blue term is the only way to introduce a graviton mass into this framework. If you have the following two conditions satisfied. So they are, the first one is if you want to ask for a standard waveform equation, a standard wave equation is in this way, so which is, as we know from particle physics, is a very reasonable assumption. And also, if you want to recover general relativity when the graviton mass go to 0, so namely there is no VD-VZ discontinuity in this linearized version of gravity. So this is so if you want to satisfy these two conditions, then this is the action for the linearized gravity. But I wanted to also mention a caveat here. So this action actually has some ghost mode. But here now we just treat it as an effective theory and try to look at what this toy theory give us in terms of binary motions. So this is the Lagrangian, and if we work really hard and try to get the gravitational wave equation from this Lagrangian, you will get something like this. So you will get an extra channel to the radiation of gravitational waves, which actually is proportional to the mass square of the graviton mass. And because of this extra radiation, the size of the orbit is decreasing more rapidly than what is predicted in general relativity. So because of this theory prediction, and on the other hand, we have a lot of binary pulsars, have a lot of binary pulsar observation. They basically show no deviation from general relativity. And by using all this data, we performed a Bayesian analysis with many the best measured binary pulsar systems. So this is a work done by my student Xuelin Miao, and we put a very good limit on this linearized fields poly theory. So the result is also collected in particle data group, the booklet that is very useful for particle physics. So this is the idea is just to constrain this extra radiation power in this particular theorem. Okay, so now let me give you a second example. This is the cubic Galilean theorem. So this cubic Galilean theorem is designed for cosmology because it has a screening mechanism which can avoid deviations for the solar system and so on. So this is Lagrangian for the cubic Galilean. And here, again, the first two part is from general relativity. And then this pi is a scalar field from this theorem. And this pi introduces extra interactions in the gravity theory, and is very useful to explain some cosmological observations. Okay, this theorem actually the higher Claudian Deham et al. They have worked out gravitational wave radiation in this theorem. They found that there are extra radiation channels, and including the extra quadrupole radiation, and also dipole radiation, and also some besides the prediction in general relativity, there are also additional quadrupole radiation in this theorem. And you can plot this radiation and their effect on the observed PB. So this PB is the binary orbital period. So these extra radiation take away energy and makes the PB decrease faster. And depend on the value of orbital period, the degree of this orbital period is different for different systems. So you can basically plot if we given a system with PB and E is the eccentricity of the orbit, you can basically predict what is the additional contribution to this time derivative of orbital period. Okay, so here I just show you the radiation power to the gravitational waves in general relativity and also in the extra monopole radiation and extra dipole radiation and quadrupole radiation. So here you can see for these extra radiations, they depend on some constant parameters here. So here beta, C1, and lambda, they are just some constant. And also it depends on the screening radius, here R star. And also it depends on a summation of some eccentricity mode functions, which I will show you on the next slide. So these are the prediction from the cubic Galilean theorem. This is the prediction from relativity. And as I said before, we have very good data to compare these predictions. Okay, so here, as I promised, I show you the eccentricity model functions that comes in this extra radiation terms. So here, basically, depend on different n, and you can sum them up and get some stable extra model functions to this contribution. So by constraining this extra radiation, actually we have collected a lot of binary pulsars. So here we mean I and also Novotovix in Germany, and also this Professor Zhou Shuangyong in China. So we have collected a lot of the best well-measured binary pulsars, and try to look for the extra contribution from gravitational waves other than the quadrupole radiation. So basically, we can put a limit from all these binary pulsars, and the best limit we got is 2 times 10 to minus 28 eV. So this is the best limit on the graviton mass in this cubic Galilean theorem. This result is also collected in the particle data group. Okay, we also, this is for the already existing binary pulsar systems. We also investigated whether future observations from binary black hole systems and the binary and the pulsar Sagittarius A star system. So here, Sagittarius A star means the supermassive black hole in the center of our Milky Way. There is a black hole which is very massive. It's 4 million solar mass. So if we found a pulsar in orbit with Sagittarius A star, or we found a pulsar around a stellar mass black hole, we will be able to perform even better limit. We can we do some prediction for based on what kind of system we can observe. So here I show we can still improve the limit by about 2 orders of magnitude, depending on what kind of system we observe. So this is actually a very active field, because many groups for pulsar observation, they are trying to search for pulsar black hole systems, which will give a very good test on fundamentals of gravity theory. For example, the Noetherian theory for black holes. So here, just another example that these systems are very good to constraining the mass of graviton. So here, now we have many new instruments. Meerkat is in South Africa, is already working, and FAST is in China, and SKA will be built in South Africa and Australia. It's the next generation radio telescope, which has a very good properties to observe this kind of system if they exist in the Milky Way. Okay, so let me give a quick summary of what I have said. So first of all, testing fundamental physics is very central to the development of human beings' knowledge, and very much rewarding, because in the history, so every looks like a very tiny advance in the our understanding of particle physics, of fundamental physics. They really get evolution to our society and also to physics. So this is very, very important to test fundamental physics. Also here I showed one particular example using binary pulsars to test gravity theory. So astrophysics actually usually it's different from experiment that is done on Earth. You cannot control what how the pulsars move and these things. You cannot control. You can only observe, but they actually provide some very unique environment for testing fundamental theories. So in this sense, they are very complementary to the experiment on Earth, and they actually did very well in many aspects. So here I just showed you the observation of binary pulsars, and actually, as you are well known, the observation from gravitational waves and also black hole shadows, they also provide very, very important information to fundamental physics. So astrophysics is very useful to test fundamental physics. Okay, so the last I want to see is we can, in principle, combine what we have done in on the Earth and what we have observed from the sky, and this combination sometimes will constraining a very significant portion of parameter space, because these two kind of experiment, they are complementary in many aspects, and they probe different portion of the parameter space, and by the combination, they will put a very, very good limiter on the theory that you want to work with. So this is basically the end of my talk, and it's important to understand using different ways to understand how the universe works and what is the boundary of our theorem. For example, for this workshop, we are very interested in what is the boundary of the graviton mass, and also what is the boundary of the black hole physics. So this is very, very important, and I think it's very, very good to have such a conference to discuss this very important question. So okay, so the last slide I want to show you in the field of pulsar astronomy. This is the next generation telescope that will be operational very soon, because this telescope is called Square Kilometer Array. It's built in South Africa. Part of it is in South Africa, and part of it is in Australia. And they are basically arrays. They are small telescopes, but they can be combined to give a very, very good very, very good sensitivity, and also very large field of view, which is very good to search for new systems. And also the survey speed is much, much better. So this is an international effort. There are more than 10 countries involved in this project, and it is really the next generation to advance knowledge in the field of pulsar astronomy. So this is under construction, and the result from this square kilometer array will come in in about a decade or so. So thank you very much. This is my talk. Thank you. Yeah, sure. Yeah, I think this is a very good idea to have two gravitons. One is massive and the other is massless. And actually, these are very important for cosmological observation, because some massive gravitons, they can explain the acceleration of the universe, and which is now we call the dark energy. Basically, we don't have much idea of what the dark energy is. This is maybe one of the idea to explain these things. And also to have two gravitons, there in most cases you will have some modification to the already existing experiment. But if you have really carefully designed the theorem, and you will have ways to avoid to conflicting the existing observational result. So overall, this is actually a very good idea to have two graviton and one with one massless, which can produce what is observed in general relativity, and the massive one will produce some effect that is important to cosmology and other aspects. Yeah, I think it's a good idea. Thank you.
Thanks to Lijing for this great speech. If possible, provide us with your speech file so that we can share it with the participant. If there is a question, you can open your microphone and ask your question.
I have a question here.
Hey,
please.
Yeah.
Thank you very much for your good presentation. I have a question about the reasons of the shrinkage of the binary pulsars. Can the shrinkage of pulsars due to other physical phenomenon like accretion of matter into from environment into binary pulsars, or dynamical friction between binary pulsar and dust of the galaxy? We just speak about gravitational waves effect. Thank you.
Yeah, thank you very much for the question. Actually, the pulsars, they usually has a lifetime of giga-years. So, which means they are moving in the Milky Way for giga-years, which is a very, very long time. And if there exists some like ultralight boson and some dust, and they can actually, sorry, I was lost connection for a few minutes. Can you hear me still?
Yeah.
Okay, sorry. My internet was down for 10 seconds. So I was saying that the pulsars, they have a lifetime of giga-years, and they can do some movement in the Milky Way. And in this history of the pulsars, they can encounter different environment. For example, the dust that you mentioned, and also if the dark matter is made of some ultralight bosons, and the movement of this binary pulsar will also get affected by this boson field, and then if we can find some unique feature to this to our observation, and we can do the comparison between the theorem and the observation. Yeah, I think this is some very nice aspect to probe. Yeah, thank you.
Thank you, Pierre.
Thank you.
Thank you.
I have a question. May I ask?
Yeah, please.
Yeah, of course. Please.
Okay. Thank you very much for your talk. Well, I have this question about. I've read in textbooks of general relativity that the observers in general relativity must be in free fall. So, but as far as I understand, you compared the results with atomic clocks, and well, they're in their laboratories, so they're not in the free fall. So, do we have a problem here, or I don't understand it? Could you please explain this? Thank you.
Yeah, thank you for your question. It's a very good question. Indeed, we compare the arrival time of these radio pulses, compare them with the atomic clock on Earth. And as you said, the rate of this atomic clock, they are affected by the gravitational potential of the Earth. And this effect actually, on one hand, they are observed by some other experiment, by some satellites carrying the atomic clock around the Earth, and they are tested. On the other hand, we have a very good understanding of them, and even they are not in the free form, we can try to subtract this effect and to get some, from some theorem and try to get some result there. And these effects, they can be taken care of because we have a very good understanding of them. Yeah, although they are not in a free fall state. Yeah, thank you.
Thanks again. So I have another question. These calculations in any modified gravity, for example, a massive gravity, they should be done in post-Newtonian formalism, or I don't know, because I remember in the works of Wheelan, his collaboration, okay, they usually use the post-Newtonian approximation. So do you do the same here, or you just use another approximation? Thank you.
So here, for massive, so for a gravity field, for a gravity theory with a massive field, the original parameterized post-Newtonian framework is not enough. So basically, because now you have a scale which is related to the component wavelengths of the graviton. So then you need to develop some new framework. So here, what was done by De Haan et al., they actually used some multiple expansion of the theory, and this is why you get this interesting, this eccentric mode functions. So you do the multiple expansion and you sum up to from zero mode to the infinity mode, and this is another method. The spirit is the same as the post-Newtonian expansion, but there are some technical differences here. Yeah, thank you.
Great, thank you.
Thank you.
Thanks again for Dr. Lijing. I have to point out that there is a very small change in the schedule, and about an hour later there will be a speech by Dr. David Mota, and the meeting will be at the Google meeting.